Hello, this video is going to focus on basic graphing in R as well as basic summary statistics. So to get started, you'll want to make sure that you have run your code up until this point. We're using the same script that we started with before, and so we have redefined variables above as part of our previous video series sessions. And so now we're going to take another deeper dive into our data set. And so if you haven't already, do make sure to open up the files BMX 2018 and Demo 2018 and send that information to your objects BMX and Demo. And do make sure to merge them as well as to clean your data in the way that we did down in section 3. So you've gotten to a point where you have actually cleaned your data, you've opened it, you have a little bit of sense from the numbers, but maybe you'd like to look at your data a little bit and get a real understanding of the visual representations of your data. And so we're going to talk very briefly about some functions in base R to do graphing. There is another graphics language that is very popular that's called ggplot2. It's an excellent language and a lot of people use it. However, in order for us to just stay focused on understanding base R language, we're going to stick with base R graphics for this video. Here in lines 340 to 341, we're using a function called hist, which will develop a histogram of this variable called BMI2. We'll go ahead and run it. And you can see what we've done. And this allows you to see what is happening as R is thinking. First of all, R is taking the element BMI2 that's located in object full data, and it's running a histogram. It's also making the bars inside of the histogram a gray color. It is also adding a label to the x-axis called BMI, which you see down here, and it's adding a label to the y-axis, which we call count, or how many people have this, this level of the variable. And we've also added a title at the top called distribution of BMI, which we have identified here as main. So certainly it's great to look at the histogram of an outcome or a measure, but it might be also very helpful to take a look at the distributions across measures of interest. In this case, we're looking at how the average level of BMI or and as well as the distribution of BMI may or may not vary by levels of family income. So we're using this function called box plot, and we are comparing average levels of BMI across levels of family income, and we're taking these values of BMI and income from our object called full data. So we're letting R know we have these two measures that are coming from the object full data, and we're adding titles and labels as detailed over here. I also wanted to bring this to your attention because up until this point, we've really been referring to variables using the object name, $sign, and that element name. But in this instance, the function allows us to work in this way. You can just refer to the names of the variables themselves and guide R to which object these variables belong to. So if you want to go ahead and run lines 343 and 344, you can see now the box plots for obesity, or BMI rather, across income levels. So you can see now that we are seeing our plots as we make them. The other nice thing is after you make a plot, you don't lose it. It's actually in the memory of this window, just using this left arrow and right arrow up here in the top left-hand corner of this window. But maybe you want to share with people outside of, that are using R what your images look like. One way to save those images is by using a viewer and exporting that to your viewer. So we have code here that says, okay, I want you to open up a file that's going to be a PDF file called testpics.pdf. And from here on, any figures that are produced will go directly to that file. Because we're using the exact same figures that we did before, what I'm going to do is actually clear all the plots from this viewer. So you can see that there's nothing here. And then I'm going to run lines 351 to 361, and I'm going to run those same figures. So we ran the figures, and what you can see is no figures appear. Now, if I open up the location of where my working directory is, I have a file here that I have called test pics, because I'm looking in the wrong file. Here. And if you see, I now have a Word document with my pictures. They're ready to go. They're really sharp and crisp, and then they can be copy and pasted into other documents or into presentations if you like. You can also copy and paste straight from R into your presentations. That's certainly a way to do it. R offers options to export here as well. Sometimes the pixelation and quality of those images varies, so test your images once you paste to see if you're happy with the quality of those images. Okay, and when you're done making figures, all you have to do at the end of your code is just type in dev.off, and that turns off any kind of additional figures being produced to that PDF file. The other thing that I want you to take note of is that right now, all of our images have been developed in this plot section with a white background, and you can only see one picture at a time, kind of a cell of a 1 by 1. But you can modify that, and you can modify the look of how you see your pictures. So we can use this, we can do this modification using a function called PAR, parameter setup. And in this case, I'm going to change the background to gray. You can't see anything now because I haven't actually run a figure. But then when I run a figure that I have here on 360 and 369, lo and behold, you have that gray background, which is different from what you had before. I can also change the output setup. I'm going to go back to white for my background. And I can now also use this par function to go into another area of detail that changes the orientation from just looking at one picture at a time to looking at two pictures at a time. And what we're saying here is we would like to see our pictures as being one row and two columns for our next set of pictures. So we'll run that, and then we will run our next image. of BMI. And now you can see that I have one image on the left, and now I'm going to add a second graph of BMI and family income on the right-hand side. So now I can see both of them on the same screen at the same time, which may be nice if you're trying to see a lot of variables at the same time. That is the super duper quick exposure to graphics. And now you have had a flavor of how R thinks about data, how it thinks about how data are stored. And now we're going to move into summary statistics and taking our knowledge a step further and really understanding things like the distribution or beyond. We've already been exposed to the concept of the summary function, and as a reminder, that really just gives you the min, max, median, and mean of a variable. We've also looked at the mean of a variable, and of course, if you can calculate a mean, you certainly can calculate a variance, and you could calculate a covariance between two variables, like I've coded here on line 399. And you'll notice that in the covariance statement, I've also included another statement called complete.obs. The function cov will ask for more information about what to do where data are not complete for both variables. And complete.obs says, provide me the covariance between two variables while removing any missing individuals so that you have complete data. There are other options that you can explore, but I also wanted to bring your attention to this. That same logic is used when you're calculating correlation between two variables using this core function on line 402. So I'm going to run that core function, and you can see here the correlation between age and arm circumference. So those are really nice for beginning to understand continuous measures. But of course, life does not always work in variables that are continuous variables. So it also helps to understand and look at the summary statistics of ordinal, categorical, binary variables. And we can do that using a frequency table. And we've seen the table function before. So we know the number of people who are, gender of 1 or a gender of 2. And we've also asked for the counts for the people who are missing to be included using the use NA statement inside of the table function. Now you can also do a cross table between gender and marital status, as we've done here. And again, these are just the numbers, the counts of people who fulfill that those categories. However, what we really like to know is proportions and not just counts. So in order to do that, I like using a package called Desker, and inside of Desker, there is a function called cross table that for people who are coming from either a SAS or SPSS background, the formatting of these results will look familiar and feel familiar to you. So if you have not done so already, you can go ahead and install the package Desker and require or open up the package for use in your R session now. Once you have opened up Desker, you can then use this function called cross table. In this case, I'm doing a cross table between two variables, gender and married. I'm also saying I'd like to see these results as a SAS format table, and I don't want to see anything related to the missing data. And I'd like for SAS to also, R to calculate a chi-square for these two variables. So everything seems to have come out fine. If I had not done that, and I had taken this missing dot include out and run it again, what you can see is that it just runs those variables. Had we included some sort of other category for missing, like NA or NA, then we might have had a problem. Okay. So now, if we have the variable rid age year and we want to describe it, we can, and we've done this before. And we could also pull out the quartiles based off of what we've learned. And we can also do things like doing chi-square tests between two variables, as we've identified here, using chi-square dot test. Optional questions to test how comfortable you are with these statistical procedures if you're learning statistics. But because this is an R coding session, I'm sticking with everything there is to understand about R. Some of you have also interest in knowing whether or not the average value of something is variable between two groups. So you can run a t-test. And in this case, we have run a t-test between people in group 1 or obese versus not obese as it applies to height. We have previously run a correlation and we're just doing it here again. And we can also include a test of statistical significance of that correlation using the function core test. So here we have not only the correlation itself at the bottom, but we also have the p-value attached to it, as well as the 95% confidence intervals around that correlation. Note that this is specific for Pearson's correlation. You will need to identify other ways to test significance if you're using any kind of polychoric correlation, for example. So that gives you a sense of some of the basics that you can do with respect to statistical summary statistics in R. And by this time, you might start thinking, well, I'm ready to run a model. And you can certainly do so. So we're going to take the quickest of introductions to linear and logistic regression modeling. This will not be an introduction to regression, but rather how you code for these kinds of regressions. And in R, it's pretty basic. If you're doing something like a logistic regression, you can use a function called GLM. This is an extremely powerful function that allows you to do regression modeling, and you're doing your regression between age and obese, with obese being measured as a binary outcome, and your data are coming from the full data object. And to denote that you are going to be using a logistic regression, you are also noting that you have a logit link for this regression model. You could run everything to the right of the arrow and say, I want to run that regression. And you have all the results there, but you may want to work with them more than just looking at the results. And so you say, I want to run this model, and everything that comes from this model will be contained in this object log fit. So if you were to run line 489 all the way through, you don't see the results of the model anymore, and you would need to see the a summary of log fit. And in fact, the view is a little bit more interesting from a summary of log fit because it shows you what model it ran. It gives you some basic statistics on your measure, at least on the residuals of this model. And then it also gives you the beta values from the model of on the relationship between age years and obese. And it also provides the statistical significance of that beta value. You also get some measures of model fit, in this case through the measures of deviance here, as well as indications of degrees of freedom. So when you look at a summary of log fit rather than just the model results, it can be quite helpful to seeing the full set of results. The other thing is I mentioned that you could potentially work with these data later, remembering that log fit is an object that contains all the information that is contained in the results. So if you were just to look at the object log fit, as I'm doing here in the console, and open it up, you'd see the results like we've done originally. But it's an object, so you can still use functions that you've learned previously to know more about that object, like names. Now you can see that there are all different kinds of elements that go into this object log fit. So maybe I just want to look at the coefficients, the beta values of that model. So I might say coefficients $sign log fit. Log fit $sign coefficients. So now you see the intercept and the beta value for age. And now you don't have to do much else, or if you want to you want to think about honing in on those a little bit more, you might say, I want to look at just age year. So I might do the value 2, add 2 to the coefficients, and now I'm only looking at the result for age. And in doing this, you're able to really hone in on just the data that you need. And that can be very valuable when you're reporting results, which we're going to talk about in a second. So we've talked about here in this set of results, the beta value that's been generated from this model. But oftentimes when people work with logistic regression results, they also like to have odds ratios. So you know that there is a formula that you can use to transform the beta values from a regression model into odds ratios. And we have coded for it here. And we've included 95% confidence intervals around that estimate. And so here we've got it. Here's the odds ratio for age and the related values for the 95% confidence intervals, as well as those for the intercept. Now, one of the things that we also have to think about is that not all of our data are continuous on the predictor side. So it's helpful to start thinking about um, using different ways of recoding and putting reference levels. So in this case, I am hard coding what obese is, the outcome is going to be by recoding in a way we've done before, obese from 0 to 1 to be a value of 1 to 2. So I've done that on line 506. On line 507, I'm also giving instructions to say, I would like that for you, R, to make 2 the reference group for, for obese 2. So now, if I want to change the reference level to be something else and I want to let R know that, I can do a couple of things. In the case of obese, it was originally coded as a 0, 1 variable, but now I want to change it from a 1 to from a 0, 1 to be 1 and 2. And I am doing our good old recode function from before to make that change. I'm also defining for R that this variable, the new variable obese2, is a categorical variable, has no order. The other thing that I'm going to do is I'm going to re-level this factor, because by default, R will make the reference value the lowest value. And so it would have made 1 the reference value. In this case, I'm asking it to make 2 the reference. And this only works with factored types of variables. So when we run lines 506 and 507, that seems to work out okay. And then when we actually now use this recoded variable, it runs it, and let's take a look at the results. And it does give you slightly different results from what we had before. Let's see. Instead of positive 0.05, we now have a negative 0.05 because we've made the reference different. This can happen on either side of the equation. It doesn't have to just be on the outcome side. We have a similar approach if we wanted to do a regression using race. So very, very similar to what we had before, and we can run that. And then if we wanted to do some sort of linear regression, we can continue using this GLM function, and we can add a couple of things. So first of all, our BMI value is one that's continuous, so that's what we're using as our outcome. And now we're going to measure the association between income and BMI while accounting for several other factors, including gender, marital status is married to, and then we're taking those from the full data object. So all you have to do when you want to add more terms into your regression model is to simply add the plus sign between your elements, and you can now have new factors in your model. You'll also notice here that I've combined this re-level function from before into the model, and I've said, hey, I want you to include this variable family income, and I want you to make the reference group the highest income group of 4. Again, because by default, it would have chosen 1 to be the reference group. The other thing that I want to bring your attention to is that I have identified that these variables are factors. If you do not do this, R will assume that your measure is continuous, and it will treat it as such. Consequently, if you want your variable to be treated as a categorical variable, you need to give this as dot factor function to denote to R that you're dealing with something that is not continuous. Let's give it a try. So now when you look at the results, I want to bring your attention to a couple of things. One, we've noticed that we were the ones to define the reference group as 4. And so what you're seeing is this is the estimate for for group 1 compared against 4. The beta estimate of group 2 compared to 4 and 3 compared to 4. Similarly, this is the estimate for females compared to males and married versus not married. 1 versus 0. So in that way, we see where this is, going and how it's treating categorical variables in your model. Okay, it's all been really great to be able to use R inside of R, but soon you're going to want to share your results outside of R. We've talked about sharing figures using PDFs and moving all your figures out into PDFs, but what about results? One, or even data sets. So let's say now you have cleaned your data to the point that you're happy, but you want to share it with somebody, or you want to analyze this data in another software. What you can do is a function called write.table. Write.table will take the object that you've been working with, in this case full data, and it will send it out to another file of your naming. In this case, we're calling it trainingdata.txt. As you know, I prefer to actually use comma delimited files, so I'm going to change it to a .csv, and then I'm going to add a couple of other things to keep at the top of your head. You're going to want to also let R know that you have variable names as your first row. Unlike read.table, when you write .table, you need to say call.names is equal to true. So it's saying, yeah, I have column names here, and I want you to honor that and make that the headers. Also, it has the option of doing row.names. Would you add, additional names to the rows or some numbers? In my case, I don't have anything, so I want to make that equal to false. And we need to give it a separator, so sep equals comma. There are other functions that you can use besides write.table. I just like write.table because it's really generic and you can type in all the small details that you want to type in. So that's what you would do to output. And so now I'm going to output this full data object into a file called trainingdata.csv. And I'm just going to see if I can open it in my working directory folder. You can see it here. When I click on this, I've opened it up in now Excel, and you can see that it has all the columns and rows as you would expect. So that's for training data, and that's how you can output your objects after you've cleaned them into data sets that can be used elsewhere. After that, you might want to report results. You might want to see individual results. So right here, I've done a write.csv to take a look at the results that we have generated from our last regression model. So as a reminder, if we were to just take a look at this middle part, COF summary log fit 4, if we look at that, we can see that these are the results that would come out from that model that we ran. This is what we see in our console. So if we're happy with that and we want to then put that into a nice table inside of Excel, we can totally do that using the write.csv. And this function is more generic to writing CSV files. And I'm going to say, take those results that I asked you to put together, and I want you to push them out to a file called trainingoutput.csv. And when you open that one up, now you can see that you have your results as you in another program to mess around with and make much prettier and easier to use. So that is a basic for getting your output out, for basic data analysis. I hope this was helpful. Please feel free to ask questions going forward by email, and I'd be happy to answer them. Thank you so much and have fun.